easier because they are, or this one's a middle riddle. So let me see what this one is. All right, let's, oh no, this one's a riddle. Let's try this one. I think this one might be a little easier. So we have a circle, with a fixed chord. So I'm going to delete B and C, and we want to fix the circle. So how about this? Actually, so yeah, I'm gonna call this D and then hide it. And A is a point on the circle, and O is the center. Although we don't even really need the point O. M is the midpoint of BC. And we have 2 points on AB and AC, those two rays, such that angle BXM is equal to angle CYM. So what we could do, here's how we could do it. We could take this whole circle and we could reflect it across the perpendicular bisector BC. And then we could try to see where it meets the other. So, oops. So let's reflect this circle about this line. And this would be the other point. So, but we want to make it intersect. We want to make them intersect on the same side. Yeah, so let me delete this. Yeah, we wanted something like that. Maybe if I make this a if I make this a taller triangle, it might be easier. So yeah, I keep forgetting the circle is fixed, so I can't, but that looks okay. So this, actually, I might just leave these circles here. So this is X. And this is Y. So angle BXM is equal to angle CYM. And then we take the circumcenter of AXY. And the theorem is that as we move A around, if we call this O prime, and we look at the trace of it, I'm going to draw this then, because basically these are both right angles, right? So that could be helpful.
This is trivial, right?
Oh yeah, because this is or wait. So
yeah,
we know
you take a homotopy at G. O prime is midpoint of AG.
Okay, so O prime is the midpoint of AG, and G
is fixed.
G is fixed. Because G lies on the perpendicular bisector of this. And
yeah, G is just like a random point on angle bisector, and when you take those two circles, they will define exactly this angle. This angle, that constant angle, and basically that's it.
Okay, so yeah, that basically solves it. So I'm gonna write it up really quick. So let BXM and CYM intersect at G. So first of all, the circles have the same radius. So I'll say that. So G, so how do we know? Oh, because BM equals CM, how do we know G lies on the, because we know G lies on the perpendicular bisector BC. How do we know it lies on the angle bisector from A?
It does not.
Yeah, I don't think it does. Okay, so we still have more work to do to solve it, right?
No, I don't think so.
Oh, so G.
So let's say we intersect this at G, then we have that angle BXM is CYM, and that is a constant, let's say alpha.
Okay.
So angle BGC would always be 2 alpha, regardless of where we take point A. And
yes.
basically, we would have that G is a constant point. It lies in the perpendicular bisector.
Okay.
It's obvious that it lies on the perpendicular bisector.
Okay. So really, yeah. So it's obvious that it lies on the perpendicular bisector, and so angle BGC is constant. So really, there's only one choice of, like, really A. If this is constant, then really, is there only one place that A could possibly be on the circle?
No, A is moving point on the circle.
Okay.
It is. The problem is that you drew those 2 circles where you like didn't fix G but fix X. That is why G is moving on a diagram and you're moving point A.
Okay, so you're saying G, in theory, G would not be moving. Well, okay, so if X and Y were fixed, then when I move A, yeah, the problem is if X and Y were really fixed, then when I move A, G would stay the same point. I see what you're saying. Okay, so we have angle BGC. So yeah, it's a homothety from G to this circle with ratio half. That's what you're saying. Yeah. Okay. That makes sense. Okay. So yeah, Ryan just mentioned it to me in the chat. So angle BGC is equal to angle BGM plus angle CGM, which is 2 angle BXM, which is constant. And so this implies G is fixed as A moves. A moves. Oh. So O prime trace it. So O prime is the midpoint of AG. O prime traces out the circle with, I'll say, homothety ratio 1/2 of O about G. All right. So I'll move on to the next one. But yeah, this one, yeah, so it took me a while to see it, but yeah, it's not very difficult. We could try this one. Let's see how hard it is. So it's an earlier riddle. So I think the earlier riddles might be easier. I'm not 100% sure. So oops, didn't want to do that. So E is on AC and F is on AB. And EF is parallel to BC. And then we have this circumcircled AEF, whoops, F. Then we draw the circle. And B is the center. And L is on BC such that LEF is tangent to BC. So it's kind of like, we could try drawing a circle like this. So we want the circumcircle of LEF to be tangent to BC. So how do we do that? Well, it would just be the it would be this circle, right? And this is L. And AEB and meets AFC at G. So that's AEB and then AFC, and they meet at G. And we want to show that ADLG is cyclic. Okay, this one doesn't look that bad. It's interesting.
I think you can just hide the circle LEF since L is just
Yeah.
BC such that LE equals LF.
Yeah, I agree. So I don't know the best way to draw this, but yeah. Or I could just say, yeah, it's the perpendicular from B to EF meets BC at L. That might be an easier way to do it. So yeah. Is AG perpendicular to BC? No, I don't know why I thought that. So yeah, it seems like a really simple problem. Let's see, I wonder if these two meet. No. So let's see. What could we use to do this? So we could try to use the power ratio lemma, right? Because then we'd have 3 circles. So what's the ratio of the power of D with respect to these two? And then what's the ratio of the power of L with respect to them? So I kind of like that idea. See what their centers are. So basically another way to
AG
say
is the median line. ABC.
AD is the median line.
AG is the median line of triangle ABC.
AG.
AG. Yeah.
Okay. So I think there's another way to phrase this. So the ratio of the powers of D with respect to both circles is going to be AK over AM. And the ratio of the powers of L, oh no, not quite. It would be DK over DM. We want to show that DK over DM is LN over LO. That would be equivalent to the problem. I'm not sure if that's that helpful. Oh, this is a generalization of IMO shortlist 2011. Interesting. So AG is the median. What's the spiral similarity that takes LO to DM? I guess it would be, yeah, I'd intersect those two at a point, and then I'd take the two circles. And that would be the center of that spiral similarity. LPO. Oh, our LGPO and DGPM cyclic. Okay, if that's true, then I think the problem might be not that bad. So can we show LGPO as cyclic? And can we show DGPM as cyclic? Yeah, if we can show that, maybe that's just an angle chase, then I think the problem might not be that hard. So yeah, something's going on here. And all the points are so close together, maybe it'll help if I move stuff around. I'm going to delete H and I for now. So yeah, can we show LGPO as cyclic? Maybe that's obvious. Can we show GOP as GLP? That feels like an angle chase, probably. Draw the tangents is T. Okay. Okay, so if we draw the tangents at E and F, and it looks like they pass through these points right here, right? So maybe, okay. So these intersect at a point T. I don't know if it's obvious that the TE meets BC at N. Oh, you show both of those are cyclic. Okay, so let TE meet BC. Okay, I'm going to delete some of what I did. Because I think Ryan has the solution here. So this meets it at N. Okay. And yeah, and obviously, yeah, BL and T are collinear. Okay, so AEBT is cyclic. Then we can use power of a point. So let me first think about that. So AEBT is cyclic. Sorry, AENB is cyclic because this angle will be the same as angle A. So this angle TNB is TEF, which is angle A. So yeah, that's cyclic. And then, yeah, similarly, this will be cyclic. So those will meet, and I can get rid of M. I can get rid of O. Seemed like an interesting idea, but I don't think we need it. So then we can use power of a point, and then that solves the problem. Okay, so how do we know that AG is a symmedian? I think
AG is symmedian. So
how do we know that?
Can you draw the altitudes from G onto AB and AC?
Okay. Oh, I think I've seen this before.
So there is a property that if the ratio of the altitudes of a point is equal to the ratio of the size of the triangle, then we will know that that point lies at the symmedian.
Yeah.
So if you call that point right there, yeah, the intersection. If we know that GI over GK is equal to AB over AC, then we claim that G lies on the symmedian line.
Yeah, I know that. I know that lemma. So
okay, so we know that triangle GBF and GEC are similar in the same orientation.
Yeah.
Since the spiral similarity at G takes B to E and F to C, and it also takes I to K. Then we know that GI over GK is BF over EC, which is also AB over AC since EF and BC are parallel.
Okay, so GI, a spiral similarity takes takes GBA to GAC, is that right? Well, because if GBF is similar to GEC, then
well, you can just explain it like how I did in the chat, like using similarities.
Okay, so by an angle chase, yeah, GBF and GEC are similar. So GEC are similar. And then once we know that, I corresponds to K in these triangles. And so GI over GK so yeah, in the chat you mentioned GI over GK equals BF over CE. Over AC, and that means that G lies on the A symmedian. See if that works. That's not great. Okay. G lies on it. So let the tangents to AEF at E and F intersect at T. T. Let T E and TF intersect BC at H and N. Hopefully this will be okay. So A, G, and T are collinear. So G lies on this median. A, G, and T are collinear. And then by angle chasing, AENB and AFHC are cyclic. And then we have by power of a point, TH, so TG times TA is TH times TF. Well, sorry, not TH times TF. TG times TA. Okay, so TG times TA is TH times TF. So wait, how do D and L? Is TL times TD. DFH is 90. Oh, okay. So that's what I've been missing. So DFT because DFLH is cyclic. DFLH and DENL are cyclic. DFHL. Cyclic. So TH times T, so TL times TD is equal to TH times TF. Thanks for helping me out with this. I'm not as smart as I used to be, which is TG times TA. That means that ADLG, say T, or not T, ADLG is cyclic. All right. That was a fun one. So we have about a half hour left. Let's see what else we can do. We got that, we got that. This is kind of interesting. This is a newer riddle though. So it's, oh, anti-Steiner point. It's probably gonna be harder. Let's try this. This one actually looked kind of fun. So we have AX is perpendicular to AB and AY is perpendicular to AC and BX. Okay, so we draw the circle ABC and we draw the tangents at B and C. Tangents. AX is perpendicular to AB. Yeah, so I'm gonna change the diagram in just a second, but this, and we see where it intersects the two. This looks a little familiar, this configuration. I feel like we might have done it in another video, but I don't remember it exactly, so should still be a good opportunity. So yeah, ABC, we can make like a smaller triangle, and then those are X and Y. Okay. So this is X, and this is Y. Then we draw the antipode of A. So X, Y. Draw the center of this circle. Oops. And reflect A over that. Ah, it's annoying. Okay, so this will be P. And then we drop a perpendicular from P to BC. And we get T. And we want to show X, Y, and AT are perpendicular. All right. So D I will call O. All right. And hide a couple things. Oops, didn't want to hide that. All right. So these are tangent. I don't know if it's worth intersecting them, but if you guys think of a way that could be useful, I'll do it. And then this is perpendicular and this is perpendicular. Maybe we could show ax squared minus ay squared is tx squared minus ty squared. Although I'm not sure if that would be that useful. Yeah, we don't want, sorry, I'm gonna, yeah. Sorry, I was trying to make it better, but maybe like that. I think that looks good. So, yeah, how do we use this tangent C? So this is equal to angle C, this is equal to angle B. This is 90 minus C, 90 minus B. So maybe it helps to draw the altitude from A, and then that would give us similar triangles. Sometimes I feel like it helps to draw this point, but I'm not going to do it just yet. So BAD is similar to CAY. And CAD is similar to XAB. and so yeah, I don't think now that we have these similarities, I don't think AX and AY, like computing one squared minus the other squared is that bad. I just don't know how to do it for T. So how would we do TX squared minus TY squared? So I wonder if this angle is equal to this angle. No. Maybe I could draw the altitudes here. And that would give me some cyclic quadrilaterals. Yeah, I want to try to use Pythagoras. That's kind of the idea, unless you guys have another idea. It feels reasonable here. Yeah, how would we find TY squared? Let's try something. So this is a circle with diameter TY. Well, I guess another way to say it is that I think the circles with diameter TY. So yeah, these circles are going to concur. I guess another way to state the problem is that we want to show A lies on the radical axis of these two circles. And can we get the power of A with respect to So that would be yeah, we know these concur. We need to show that A lies on their radical axis. So if I extend this, XA times AH. We know XA pretty well. Can we get AH? I don't know if that's the best way to go. So TXH is 90. So yeah, TH is parallel to AB. So maybe this will work because basically we have a rectangle then. So let's try that. So oops, not a rectangle. We have a cyclic. Yeah, we know this is cyclic.
Actually, if you let it meet the circumcircle ABC, then it will form a rectangle.
Oh, okay. So let me draw those points. Like that. So like that. So are X, I, and T collinear? It looks like it. Wait. Yeah. So I think if this picture is like I think it is, oh no, X, I, and T aren't collinear. So AX times AH is the power of A with respect to that circle. I forgot where I was going with that. Basically, yeah. So we have a lot of parallel lines. This is parallel to this, parallel to this, and this is parallel to this, is parallel to this. And we want to show the power of A with respect to both is the same. Oh, so I think I wanted to show that XIHY is cyclic. Yeah, because then it would be equivalent. And we want to show that XYIH is cyclic. I wonder if it's getting close to just being like an angle chase. I wonder if XYJK is cyclic. No. But AIH is ATH. So we want to show ATH is AXY. So we want to show ATH is AXY and ATI is AYX. But ATH is ADH. Yeah, because all these are cyclic right here. So I think that helps a lot. So ATH is ADH. So we want to show ADH is AXY. And I wonder if AIDH is similar to AJPK. For some reason, I don't know why, but for some reason I feel like there's a chance that could be true. Is JIHK cyclic? No. So HDA, what do we know about that? I think there's some theorem about this. It almost feels like isogonal conjugates a little bit. So we would have, we want to show this is ADH, and we know that this is this angle. So H. We want to show these angles are actually these angles. I know there was some problem that I-3435. There was some problem from like Math Without Limits from Poland, where it's like you take the antipode of A, then you drop a perpendicular, and then somehow two things are like isogonal conjugates. But I think that problem involved orthocenters. So So maybe actually, you know what? I think maybe we could use, I think Trig-Cheva might end up solving this, because if you extend, or maybe even regular Cheva, well, because we know these angles are equal. Angle XBC is angle YCB. I think somehow if you use the fact that angle XCB is angle YCB, because we keep forgetting to use that, and then somehow you use Trig-Cheva, you might be able to show the sine of this over the sine of this. Yeah, so like if we extend these two, XB and YC, can we use Trig-Cheva in a way that makes these angles cancel? So let me draw this point. This is looking like a mess now. Sorry about this. I wonder. So yeah, it looks like G, D, and L might be collinear. Yeah, it's looking like G, D, and L are collinear. No, it's not necessarily. Okay. But even if that's not the case, that they're collinear, well, that might be kind of important actually if we. Okay, let's forget that. But maybe I wonder if this and GL are concurrent. So because then we could use Cheva. If that were true. I don't think it is. No. Okay, my bad. All right, we started a couple of minutes late, so maybe we can do this like 3 more minutes. Oh, is this a right angle right here? Angle TL. So are these the rectangles you were talking about? I don't know if this is actually a... No, that's not 90 degrees. Yeah, I think so. AD and AP are isogonal. There was something about the line connecting the orthocenters being perpendicular. So,
I think I found a solution.
okay.
Okay, so can you just keep the original points and just delete the other ones?
Yeah. All right.
Okay, so I'm gonna let can you let AT meet XY at a point? Yeah, we will need point D. Don't delete it. We need point D.
Okay. Sorry.
I'm not really sure, but I'm gonna try this because we don't have time left. So hopefully I'm
Sorry.
not wrong. Okay, so I'm gonna redefine T as we let AE be the perpendicular line to XY and let it meet BC at T. We're gonna T prime and we're gonna prove that T prime is same as T.
Okay.
Okay, so we have AX over, I'm gonna do a little calculation here. So we're gonna calculate AX over AY as a cosine of XAE over cosine of EAY.
Okay.
So my point here is to calculate T prime B over T prime C, because if I can calculate that ratio, then I can prove that T prime is the same as T.
Okay.
So we have AX over AY is cosine of XAE over cosine of EAY,
Okay.
and it is the same as sine of angle BAT over sine of angle BAT prime over sine of angle CAT prime. Because we have this
because these are 90 degrees. Okay. Actually, yeah, that makes a lot of sense. Okay.
So in other words, we have ax over ay is equal to sine of bat prime over sine of cat prime. However, we have ax is equal to ab times tan of angle abx.
Yeah.
And it is ab times the tan of angle c. So we have wait, hold on a second. I'm doing my calculation. So in other words, we already calculate the sine of ta prime t prime ab and over sine of t prime ac in terms of ab and ac and angle b and angle c. So it is easy to show that t prime and t are the same point.
Okay, so yeah, I see how you did it. So I'll just summarize it really quickly. So calculate, so let the perpendicular from A to xy meet BC and xy at t prime and e, and then I'll say, so we have xe over xy is equal to EA or AX cos or AX sine EAX over AY sine EAY, and which is AX cos, yeah, okay. So I'm just going to type that out. Thanks for typing it out. And then we also have BTP is similar to triangle BAD. And so this is the original T. BTP is similar to triangle CAD using the original definition of T. Using the above information, we can show BT over CT equals BT prime over CT prime. Which means that T prime equals T, which means that XY is perpendicular to AT. Okay. All right. So I think this should be good for now. Yeah, it is pretty cool. All right, so for everyone watching on YouTube, thanks for watching, and thanks everyone who participated for their nice solutions. So if you want to join me in future sessions, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.